Hi everyone, we're looking at Text and Test 5, page 471, exercise 12.4, and proof by contradiction here. This is maybe tricky enough. The one you really want to know is example 2 on page 470, which I'll be looking at in class. That comes up a lot in tests or in exams. But I'm looking at a different one here, which is question 2. Proof by contradiction that if A is a rational number, that is, can be written as a fraction of integers, so for example 5 over 7 or something like that, and b is an irrational number, so it cannot be written as a fraction of integers. So numbers like root 2 or 2 over root 5 are irrational, cannot be written where both numbers, top and bottom of the fraction, are integers. That a plus b is an irrational number. Now we're going to assume it's rational and we're going to arrive at a contradiction. And just a note here on b, it's composed of two numbers if you write it as a fraction. So if, for example, it was root 2, that'd be root 2 over 1. I'm assuming the bottom number is an integer, and that's okay because normally where you have an irrational number on the bottom of a fraction, you'll rationalize it anyway, and you'll end up with something like 2 root 5 over 5. So you'll always change that number so that the bottom number is a rational number and is an integer, I suppose. So this is an integer on the bottom. It's not necessarily an integer on the top. But we want to prove that when you take a plus b, you get a number that is not a rational number. In assuming that it is a rational number, we'll say, well, a plus b can be written as p over q plus r over s. To put them together, we want a common denominator. It's going to be qs. So it's going to be ps over qs plus r q over qs. And so that can be written as ps plus rq over qs. Now we're assuming that this is rational, which means that's an integer and that's an integer. Okay, well, it's the bit on the top we're interested in because really what we want to show is that r has to be an integer under our assumption, and that will be our contradiction. So ps plus rq is now an integer by our assumption. Now ps is an integer because that's one integer p multiplied by another integer s. A whole number multiplied by a whole number gives a whole number answer. So that part's an integer. So the bit we're adding on must also be a whole number or an integer in order for the whole thing to be an integer. And now we're saying, well, r multiplied by q is an integer. Q we know is an integer. We were given that at the start. Okay, but the only way you can get an integer answer, if you take an irrational number and multiply it by an integer, you end up with an irrational number. For example, 2 multiplied by root 5 gives 2 root 5. It's irrational. The only way you can get an integer when you multiply one integer times another is if the other number is an integer as well. So we've arrived at this conclusion that therefore r must be an integer, which is a contradiction. So then you have to go back and look at your assumption that a plus b is rational. That's false. Okay, so we've proved by contradiction that a plus b is an irrational number. Okay, therefore, a plus b is an irrational number. That's written like this by contradiction. Okay, question 3 asks us to prove by contradiction that there are no positive integer solutions to x squared minus y squared equals 10. Okay, so here x and y are integers, positive integers, which makes them natural numbers. And you need one to be bigger than the other. I'm going to assume, well, x has to be bigger, doesn't it? If you're taking y squared away to get 10 there. Otherwise, you get a negative answer. So x is greater than y, and we're going to assume that, sorry, this is what we're assuming, that x and y are both integers. Well, let's see, what does that lead to? X squared minus y squared equals 10 can factorize to x plus y times x minus y equals 10. And dividing through, you get x minus y equals, 10 divided by x plus y. Okay, so the argument that I'm about to make is that this number is not an integer. Now, if you take a whole number and subtract a whole number, you should get a whole number. Okay. Now, the only way that this could be an integer, a whole number, is if x plus y equals either 1, 2, 5, or 10. It can only be an integer if x plus y add up to give these factors. Okay, well, what are the combinations? No combination of whole numbers will give 1. Well, you could say 1 squared, take away 0 squared, but then there's no way to get 10. Okay, so the 1 is out. To get 2, x and y would have to be 1 and 1, and maybe that should have been greater than or equal to. 1 squared take away 1 squared doesn't give 10 either, so that's no good. To get 5, you've either got 2 and 3, or you've got 4 and 1. Okay, so x being the bigger number, maybe I should have said 3 and 2. 3 squared, 9, take away 4. 2 squared, 4, gives 5. So it's no way 3 and 2. 4 squared, 16, take away 1 is 15. You can't get 10 with any of these numbers. Okay, this, by the way, is not a very elegant way of proving it, but it gets the job done. You get a 10 there, you might have you might have 1 and 9, you might have 2 and 8, 3 and 7, 4 and 6, 5 and 5. Okay, those are your options. Again, where x is actually always a bigger number, so sorry, maybe I should have done it the other way around. 9 squared, take away 1 squared, doesn't give 10. 8 squared, 64, take away 2 squared, 4, doesn't give 10. 21, take away 9, doesn't give 10. 7 squared, 49, take away 9. 7 squared, take away 3 squared, doesn't give 10. 36, take away 16. 36, take away 16, that'd be 6 squared, take away 4 squared, doesn't give 10. And 25, take away 5, doesn't give 10 either. So none of the numbers that could make this a whole number work in our original equation. So therefore, if x minus y is not an integer, that's a contradiction. And so we can say that x squared minus y squared equals 10 has no integer solutions. Okay, question 5 is a direct proof. It says, prove that if a divides b, that is b divided by a equals x, and if a divides c, sorry, where x is a whole number, excuse me, that's important, and if a divides c, that is c divided by a equals y, where y is a whole number, then a will divide b plus c. Okay, well, this is actually reasonably straightforward because division is distributive over addition like this. You can say, well, this is the same as b divided by a plus c divided by a. B divided by a we've called x, which is a whole number. C divided by a we've called y. So that's one whole number plus another whole number is a whole number. Okay. So the solution to b divided by c, b plus c divided by a is a whole number. Therefore, b plus c, a divides b plus c. So that's all there is there to 5. And question 8 says, prove that the sum of two odd numbers is always even. Okay, so how do you write an odd number in abstract terms? Well, if x is any whole number, twice that plus 1 will always be odd. Okay, so 2x plus 1 will always be odd. Try that, stick a 5 in. Twice 5 is 10, plus 1, 11. It's an odd number. Same thing for y, twice y plus 1. That's another odd number. So these are two different odd numbers where x and y are both whole numbers that were just any whole number you want to plug in there. Prove that the sum of these two will always be even. Well, that's 2x plus 1 plus 2y plus 1. That gives 2x plus 2y plus 2, which can be written as 2 times x plus y plus 1. Okay, and any number that has 2 as a factor is even. So that's that one proved. Okay, what I'd like you to try now yourselves is question 1 and question 4, please. Okay, and we'll finish the rest in class.